Good evening, everybody. Yesterday, I was discussing about the definition of the fluid and how to distinguish between a solid and a fluid. In the last class, I had defined a fluid is that part of matter which offers very small or negligibly small resistance against the action of the shear force or shear stress, and hence a fluid deforms continuously even under the action of a slightest shear force or shear stress. It cannot sustain even the slightest shear stress. That means whenever a fluid is in motion, there must be definitely smaller or higher shear stresses must be acting on the fluid element. The shear stress acting on a fluid would be zero only when the fluid element is at rest. A fluid element at rest is not subjected to any shear stress, but it is subjected to normal stresses, which is also called as hydrostatic pressure. In fact, in future course of coverage of the syllabus, I will be defining those normal stresses acting on a fluid element as a fluid pressure, which is defined as normal force per unit area. Pressure is defined as normal force per unit area, having the units of Newton per meter square, which is also called as pascals. In fact, fluid, anything that is in motion is subjected to, any fluid is in motion and is subjected to a shear stresses, tangential stresses, or which are also known as viscous stresses. I was discussing yesterday the fluid properties. I defined mass density rho as mass by volume, so many kg per meter cube. In fact, matter could be broadly classified as solids and fluids. A solid, as you have learnt in the fluid mechanics, could withstand even the very high shear stresses or tangential stresses also acting on the solid element. Supposing if you take a solid block like this, if you exert a tangential force or shear force on the top of the block would tend to deform in this fashion. If this is the orientation of the block before the force is applied, and after the force is applied, the block would deform in this manner. This is the deformation we can notice after the exertion of the force on the top surface of the block. So we could also call this theta as the shear deformation, which is because of the shear force acting on the top surface of the solid block, which is indicated as F. The bottom surface of the block is fixed. And this is the solid body behavior under the exertion of the shear force. This is the before exertion of the force, and this is after the exertion of the force. Whereas when you come to the fluid, it will deform even under the action of a slightest shear force, and moreover the deformation is also continuous. Whereas if you look at this solid, once you remove this force, the solid block is tend to regain its original shape and size once this applied force is well lesser than the elastic limit of the solid. If the applied force F is well within the elastic limit of the body will be able to regain its original shape and size once the force is removed. So that is the nature of the solid. Solid could withstand huge shear stresses also, and moreover the deformation is not continuous. But when you come to the fluid, the deformation of the fluid is continuous, and also the fluid cannot sustain even the very slight shear stresses or shear forces acting on the fluid. Therefore, a fluid deforms continuously under the action of a shear force. Even the shear force is very small. Supposing if you consider two plates, parallel plates, between which a fluid is expected to be existing here in this gap, and the bottom plate is fixed like this, and where the plate is fixed, stationary plate. This is and on the top plate I have exerted a very small shear force, not a bigger one, not a higher one, and I am able to move this top plate with a constant velocity v. Then the different fluid layers will be having a different velocities as they keep sliding one above the other. That means you can see that between the fluid layers that are moving one above the other, the shear stresses are exerted. One layer is trying to drag the next layer. So these tangential stresses or shear stresses will be acting between the two layers which are sliding one above the other with different velocities. There are relative velocities prevailing between the fluid layers. So, this fluid keeps on deforming as long as the shear stresses are acting. Please note that in the case of the solids, the deformation is not continuous, whereas in case of the fluid, the deformation is continuous. Here the solids can withstand very high shear stresses also. To need to have a very small angular deformation or shear deformation, the magnitude of the force that is acting on the solid must be very high. But whereas in case of the fluid, even if this applied force is very small, minutely small shear force, the fluid keeps on deforming as long as that slight shear force is acting on the fluid. So that is a main distinguishing you can see between a solid and a fluid. A fluid element at rest is not subjected to any tangential or shear stress. The only stresses that are acting on a fluid element at rest are normal stresses. Please note that, are normal stresses. A fluid element at rest is not subjected to any tangential or shear stresses. Therefore, the only stresses that are coming into picture acting on a fluid element at rest are normal stresses. We could also notice in this figure, you could also see in this figure that a fluid element at rest is subjected to only normal stresses, which are also called as hydrostatic pressure. This is rest, fluid element at rest. This is the nature of the stress. This is the state of the stress acting on a fluid element at rest. In fact, later we are going to see that these normal stresses are also called as hydrostatic pressure, and there is one of the very famous laws which you have learned in the physics also. The Pascal's law of hydrostatic pressure states that the pressure acting on a fluid element at rest is the same in all the directions. Very famous law in fluid mechanics, Blaise Pascal's law, states that the hydrostatic pressure acting on a fluid at a point is the same in all the directions. That is why I have shown the same magnitude of P here. And therefore, if you draw the Morse circle corresponding to this kind of state of stress, the radius of the Morse circle becomes 0. The Morse circle shrinks to a point for this kind of stress acting on a fluid element at rest. The radius of the Morse circle becomes 0. When the radius becomes 0, the Morse circle becomes a point on the if you draw a Morse circle, I could even draw that like this. This is the kind of state of stress as you have shown. This is the shear stresses, this is the normal stresses. So this is the kind of the stress what you can show on the for drawing the Morse circle. This is a Morse circle whose radius is 0. Morse circle shrinks to a point as you have seen in this figure. Because while drawing Morse circle, the x-axis is normal. In fact, the y-axis is shear. Because on the x-axis the shear stresses are 0. There are no shear stresses or tangential stresses acting on a fluid element at rest. So from this figure we can clearly notice that there are no shear stresses. Tau indicates shear or tangential. N indicates normal stresses, which are what do you mean by normal stresses? The stresses acting perpendicular to the plane. Now let us, having known what is a fluid, what are the examples of the fluid? You can give all the gases, all the liquids, all the vapors can be treated as fluids. Water, air, blood, milk, petrol, diesel, air, hydrogen, any gas, any vapor can be thought of as a fluid. In generally, the fluids, on a broad basis, fluids can be classified as incompressible fluids and compressible fluids. Generally, we perceive all the liquids as incompressible fluids because they possess a constant density, whereas compressible fluids change their density according to the pressure. So that is a simple broad classification. All gases can be thought of as a compressible fluids, but actually we treat even the flow of the gases also incompressible, neglecting any small changes in density. Generally, compressible fluid means if the density of the fluid is changing, it is called as a compressible fluid, or density becomes a function of pressure. Whereas in case of the incompressible fluids, the density remains constant. So that is the main classification, generally broad classification of the fluids. One should remember generally, but throughout our course of analysis we treat fluids as incompressible. In fact, the study of the compressible fluids you will be doing it in the thermodynamic analysis also, where you deal with the adiabatic process, isothermal process, where the density of the fluid will be changing. But in our analysis, mostly 99% cases we treat the fluids as incompressible, that is density of the fluid is a constant. Now let me define various fluid properties. First property what I consider is mass density, rho. Density is defined as mass per unit volume. And for standard fluid, which is water, density value is 1000 kg per meter cube or 1 kg per liter or 1 gram per cc. Cc is nothing but milliliter. 1000 cc is equal to 1 liter. 1000 liters is equal to 1 meter cube. You should remember this value, density of the water. Different fluids have different densities. Because we have learned for water, let us see what is the density of the air also. density of the air is 1.18 kg per meter cube at normal atmospheric conditions. That is 1 atmosphere pressure and usually 25 degrees Celsius. At 1 atmospheric pressure and 25 degrees Celsius, the density of the air is 1.18 or 1.2 approximately kg per meter cube. As you have seen from these values, water is 1000 times denser than air. Water is 1000 times heavier than air. In fact, mercury is 13.6 times heavier than water. Mercury is the very heaviest liquid whose density is very high. Now the second property what I define is specific weight, which is also known as weight density, but mostly I will be using the symbol W for specific weight. Very important property in our fluid mechanics. Throughout the subject we will be frequently using this property called specific weight, also known as weight density, which is defined as W. Don't think that is omega, it is a small w. Weight per unit volume. If density is looked as mass per unit volume, specific weight is weight per unit volume. Since weight is also a force, gravitational force, I use the unit Newton, because because in SI system of units, we always using SI system throughout the GATE or any kind of engineering subjects, engineering exams, we will be using only SI system of units where the force is measured in newtons, power is measured in watts. So weight by unit volume is Newton per meter cube. W of water is equal to 9.81 kilonewton per meter cube, specific weight of water. Now I could connect this specific weight with the density like this. W specific weight is equal to, weight is given as mass into acceleration due to gravity divided by volume. Mass by volume is density into acceleration due to gravity g. So many Newton per meter cube. This is density, that is specific weight. Third property I will define as specific gravity, which is also termed as or relative density. S, specific gravity or relative density, symbolized or denoted as S, which is defined as S is equal to, it is the ratio between density of fluid, specific gravity of any fluid is density of fluid divided by density of standard fluid, that is water. Because it is the ratio of the same quantity, it is a unitless, dimensionless quantity, density of the fluid divided by density of the standard fluid. Obviously, specific gravity of the water will be 1. Specific gravity of the another important fluid, this is mercury, is 13.6. Mercury is the heaviest liquid we have. Mercury has got very special properties, in fact, among all the fluids. Highest density, very low vapor pressure, very high thermal conductivity. So these are all the very good expansion coefficient of against the heating. So all these things will make a very important special fluid among all the fluids. Almost everything floats in mercury. If you take a mercury tub and throw a steel block, it will comfortably float. It won't sink because specific gravity of the steel is only 7.8, whereas the mercury has a specific gravity of 13.6. You throw anything into the mercury, it will float. Don't throw the gold, because gold does gold and mercury, there will be a reaction. Gold will get spoiled there. So that's the actually I just given the example as the mercury because it is the heaviest liquid, having 13.6 times heavier than water. So from this I can say specific weight of mercury is 9.81 into 13.6 kilonewton per meter cube. Hg is the symbol used for mercury. Nothing sinks in mercury because in fact this is the highest heaviest fluid having highest specific gravity. If you want to carry a 14 liter bucket of mercury, we need 2 to 3 people, because that will, whose weight will be 14 into 13.6. That much of weight you need to carry. You need to 2 people to carry that only simple small bucket of mercury, because that is the heaviness of the mercury. So these are the 3 important properties, and the 4th property will be even more important, called as the viscosity. Specific gravity of petrol and diesel are lesser than 1. That is why petrol and diesel float on the water. Specific gravity of petrol is less than 1. That is why when you pour the petrol on the water, it will float, it won't sink. Now I'll define another important property called as viscosity. So important. What is this viscosity, and when does it come into action? Viscosity is a property of the fluid by virtue of which there is a resistance offered by one layer of the fluid over its adjacent layer against the relative motion between the fluid layers. Now let me write the definition. It is the property of fluid by virtue of which there is a resistance offered by the fluid against the fluid layer against the adjacent layer property of the fluid by virtue of which there is a resistance offered by one layer of the fluid against the adjacent layer against the relative motion between them. Every fluid will have viscosity. There is no fluid in nature which has zero viscosity. If one layer is trying to slide over the adjacent layer, you will see the shear stresses offered by one layer against the other layer because of this basic property called as viscosity. Supposing if you take a coconut oil, if you take water, if both are flowing in as two similar diameter pipes, obviously you can easily say that which fluid can flow through the pipe easily? Water, as compared to the coconut oil. Why? Because the coconut oil has got more viscosity than the water. If you take any lubricant like SAE 60 or SAE 40, what we generally use in various bearings, hydrodynamic bearings like journal bearing, etc. If you talk about any lubricants what we are using in our automobiles, in your bikes, SAE 60 or SAE 40 oils, these oils which are known as lubricants would have very high viscosity as compared to the other kind of fluids like water. Coconut oil is more viscous than water. Lubricant is more viscous than water. Water is more viscous than air. So every fluid would have some kind of a magnitude of viscosity. There is no fluid which has got zero viscosity. If any fluid has zero viscosity, it is called ideal fluid, inviscid fluid. Ideal fluid means which has got a zero viscosity. A fluid which is having more viscosity will tend to go slower and slower because more and more shear stresses will be acting between the fluid layers, which are offering more and more resistance for the relative motion between the fluid layers. So viscosity is the property of the fluid by virtue of which there is a resistance offered by one layer of the fluid over its adjacent layer against the relative motion between them. So in fact, if you want to understand viscosity very clearly, we have to go to the very classical law called as the Newton's law of viscosity. Let me explain you about the viscosity from this law. Newton's law of viscosity, very famous law in fluid mechanics. Please note that these viscous stresses which are offered by one layer against the another layer will come into action only when the fluid is in motion. When the fluid is moving, these viscous stresses come into action. If a fluid is at rest, there is no manifestation of the viscosity of the fluid. Fluid cannot show its viscous influence when the fluid is at rest. Only when it is in motion you can see the influence, the effect of viscous nature of the fluid, because viscosity manifests itself in the form of the shear stresses between the fluid layers, tangential stresses between the fluid layers. So if we just look at this Newton's law of viscosity, if you take two plates which are positioned at a distance of capital Y, the gap between them, bottom plate is fixed, stationary plate, fixed plate. This is a fluid, the gap between the two plates is capital Y. I have exerted a force F on the top plate. I am able to move the top plate with a constant velocity V. There are two plates, parallel plates, kept at a distance of Y. The gap between the two plates is filled with a fluid. This is all a fluid. Bottom plate is stationary, therefore its velocity is 0. I have exerted a force F on the top plate and I am moving the top plate with a constant velocity V. Generally, you must have learnt in the physics also from the Newton's laws of motion. Whenever there is a force acting on a body, the body must move with an acceleration. How come the top plate is moving with a constant velocity, that is with 0 acceleration it is moving? There must be acceleration. That means this applied force F on the plate must have been balanced by equal and opposite force on the plate which is acting like this. That force is exerted by the fluid. That is the viscous force acting on the top plate exerted, that viscous force is exerted by the fluid itself on the top plate. So if you look at this, if this is a fluid, there is one layer of the fluid which got attached to the top plate. There is one layer attaches itself that cannot slip from the plate. So that layer obviously will move with a velocity v. That layer would be moving with a velocity v, and the bottommost layer which is attaching itself to the bottom plate has got a zero velocity, because the bottom plate is stationary. The velocity of the bottom plate must be, bottommost layer which is attached itself to the bottom plate, it should have a zero velocity. The topmost layer which has attached itself to the top plate has got a velocity v. The bottommost layer which has attached itself to the bottom plate has got a velocity 0. So different fluid layers at different heights, which you can indicate as a small y. This is a coordinate direction measured in the normal direction to the plate. Different fluid layers at different y values will have different velocities, which I can show that in the form of these arrows. The arrow indicates the magnitude of the velocity of the fluid layer at different y values. You can see here the bottommost layer has got a 0 velocity, therefore the length of the arrow is 0. The topmost layer has got a velocity v, maximum velocity among all the layers. Its magnitude is v. Different fluid layers at different heights will have a different velocities. So let u be the velocity at any height y. U is a function of y. Please notice in this figure that there are relative velocities between the fluid layers because of this viscous nature of the fluid. This layer has got more velocity than this. This has got more velocity than this. So in the direction of the y, the velocity magnitude is increasing. The maximum velocity you see for the topmost layer, that is of magnitude capital V. That is, u is a function of the y. There is a velocity gradient. Let dou u by dou y is the velocity gradient. Let tau be the shear stress or tangential stress between the fluid layers. Therefore, Newton's law of viscosity states that, this law states that the shear stress, we can also indicate as tau or tau h. The shear stress is directly proportional to the velocity gradient. Tau is a generally symbol used for the stress. Stress is obviously measured in Newton per meter square. Shear stress or tangential stress or viscous stress all mean the same. Viscosity is a shear in nature. That is a very fundamental thing we have to think about any fluid. Viscous stress is of shear in nature or tangential in nature. The proportionality constant is mu, dou u by dou y. The law states that shear stress is directly proportional to the velocity gradient, Newton per meter square. This is the law called as Newton's law of viscosity, stated by the same man who has stated the Newton's laws of motion. This mu, the proportionality constant mu, is called as dynamic viscosity. Sometimes it is also called as absolute viscosity. Which is a property of the fluid. Please notice that it is a thermophysical property, a property of fluid. Any fluid will have some properties like density, specific weight, viscosity, thermal conductivity, specific heat. These are all the important thermophysical properties of a fluid, which are important in thermodynamics, another subject also. Particularly when you study the heat transfer, this dynamic viscosity is an important property of the fluid, particularly in convection heat transfer. So what units you can expect for this dynamic viscosity? Mu is measured in, I am writing the units of the mu here. Shear stress is measured in pascals or Newton per meter square. Units of mu are Pascal second, or we can also call Newton second per meter square, having a dimensional formula of ml minus 1 t minus 1. This Pascal second, which is also called as kg per meter second, this can also be given like this, ml minus 1 t minus 1. This is the dimensional formula for the dynamic viscosity, kg per meter second, which is a property. I just give the, because water is an important fluid, I would like to give its value. Mu of water 0.001 approximately. It is not a constant. Please notice that the dynamic viscosity changes with the temperature. As temperature changes, dynamic viscosity also changes. This is the mu of the water at a simple normal atmospheric and temperature conditions. Pressure is 1 atmosphere and temperature is around 25 degrees Celsius. This is the viscosity value. Mu is a function of temperature, as you must have seen in your famous viscosity experiments called Redwood viscometer, Sebold viscometer. You must have noticed that, you must have observed that as the temperature of the liquid increases, viscosity decreases. In fact, what is the mechanism, what is the reason behind this viscous nature of the fluid? If you think carefully, any matter is consisting of molecules. Like any matter, fluid is also a part of the matter. There will be molecules in any fluid. There will be intermolecular attractive forces, which are also called as cohesive forces. This viscosity in liquids is majorly because of the intermolecular attractive forces called as the cohesive forces. As the temperature of the liquid is increasing, the intermolecular cohesive forces get loosened, become weaker, therefore the viscosity decreases with increase of temperature. But when you come to the gases, the viscosity is because of some other reason. The viscosity in gases is because of basically molecular momentum transfer. As you observe the liquids and gases carefully, in the liquids the molecules are much closer to each other, and there will be great amount of the intermolecular forces, attractive forces or cohesive forces. But when you come to the gas or a vapor, the intermolecular forces are very weak, molecules are very free. That is the reason why liquids possess a definite volume. If you take a 1 liter of water, when you pour in a bucket, or when you pour in a mug, or when you take in a glass, its volume is same. But it will take the shape of that container. The volume of the 1 liter of water is same everywhere. But when you take the gas, the volume, the gases occupy the entire container volume. That is because in gases the intermolecular forces are very weak. But what is the reason behind the viscous nature of a gas? It is the molecular momentum transfer, when high velocity molecules collide with the low velocity molecules. So that is the reason why in gases, as the temperature increases, the molecular activity increases, randomness of the molecules increases, the number of collisions among the molecules will increase, molecular momentum transfer will increase, viscosity increase. So I can give the reason why the viscosity of the gases increase with temperature, because as the temperature of the gases increase, you can expect number of collisions, more number of collisions per unit time. That is what you have seen in the kinetic theory of gases also.